Welcome, and thank you for finding your way here tonight. Perhaps your day has been long and demanding, or maybe you simply prefer drifting towards sleep while contemplating the stars instead of tallying sheep. Whatever brought you here, this video was created with you in mind. Allow your body to settle into comfort, your breathing to deepen, and your thoughts to become weightless, as though gravity itself has loosened its grip. Tonight, our journey takes us through cosmology, the extraordinary narrative of our universe. From its very first flash of radiance to the formation of immense galaxies, this is a story woven from vastness, enigma, and awe. Some of what follows may astonish you, or it might simply kindle a quiet sense of fascination as you ease into slumber. If these peaceful explorations bring you comfort, please consider liking and subscribing. It helps fellow wanderers discover this space, one restful mind at a time. But for now, let us embark on this voyage together. In the earliest moments following the Big Bang, the universe was neither dark nor void. Instead, it blazed with brilliance. Photons, particles carrying light, were compressed so tightly together that they couldn't travel freely through space. They collided constantly, bouncing off matter particles and off one another in an endless cascade. This incredibly dense ocean of radiation created physical pressure, behaving almost as though light itself possessed mass and substance. As the cosmos stretched outward and temperatures dropped, these photons finally broke free, streaming into the expanding void. What remained became the cosmic microwave background that envelops us even now, a faint whisper of that ancient era when the universe glowed so intensely that light behaved like matter itself. This relic radiation, stretched thin across billions of years, carries the memory of a time when brilliance filled every corner of existence. According to the theory of cosmic inflation, during its first fraction of a second, the universe expanded at speeds exceeding light itself. But certain models suggest that inflation didn't conclude everywhere simultaneously. Instead, it may continue eternally in distant pockets of reality, perpetually generating new regions of space-time that remain forever isolated from our reach. These inflating domains would grow so rapidly that no signal, not even light, could ever traverse the gulf separating them from us. In this vision, our observable universe represents merely one bubble floating among innumerable others, each sealed off by the runaway expansion of space itself. We will never observe those distant realms, never interact with them, and yet they might exist nonetheless, endlessly budding into the cosmic void like flowers on an infinite tree. The thought that our entire observable cosmos could be just one finite blossom on this endless tree feels both humbling and strangely beautiful, a reminder that what we see may be only the smallest fraction of what truly exists. Black holes are typically understood as the final resting places of collapsed stars, yet some may predate any star that ever existed. Cosmologists have proposed the concept of primordial black holes, objects formed during the turbulent chaos immediately following the Big Bang. If density variations in that fiery first instant were sufficiently extreme, entire regions of space could have collapsed under their own gravitational weight before atoms, stars, or galaxies had even begun to form. Such black holes would carry within them direct evidence of conditions prevailing mere moments after creation itself. They might range in size from objects as small as mountains to masses rivaling stars, hidden throughout the universe like ancient relics of the moment of creation. If we ever discover them, they would serve as time capsules preserving secrets from a universe younger than a single heartbeat, an era when the physical laws governing reality may have operated differently than they do today. Time feels constant to us, with each second passing evenly, one after another in predictable succession. Yet near the Big Bang, this steady flow may have been anything but simple. General relativity reveals that time and space are interwoven, and their behavior depends on the presence of energy and gravitational forces. In the searing furnace of the early universe, where densities and energies reached unimaginable extremes, time itself may have stretched, warped, or flowed differently compared to the steady pace we experience now. Some theoretical frameworks suggest that what we call the beginning of time might not represent a true origin point at all, but rather a transformation from one state of existence into another. When we peer backward across billions of years of cosmic history, we may not simply be looking through space. We may also be gazing through shifting rivers of time itself, where the very nature of temporal flow was fundamentally different. The universe is not uniform in its distribution of matter. Galaxies do not scatter randomly like particles of dust blown by wind, but instead organize themselves into vast patterns, threads, walls, and filaments stretching across incomprehensible distances. One of the most remarkable of these structures is the Boss Great Wall, discovered through extensive galaxy surveys. This sprawling chain of superclusters extends across nearly 1 billion light-years of space. Within this colossal structure, galaxies are strung together like luminous beads threaded on invisible strands of dark matter. To grasp its scale, imagine that our entire Milky Way galaxy were reduced to a single tiny dot on a map. This wall would stretch across entire pages of that map. These cosmic structures remind us that the universe is not merely vast, but also deeply patterned, displaying a kind of architecture on the grandest stage imaginable. Gravity has sculpted the cosmos into elegance, revealing hidden order across distances that challenge human comprehension. Neutrinos are ghostly particles with almost no mass, interacting so weakly with ordinary matter that they pass through it virtually unnoticed. Trillions upon trillions stream through your body every single second without leaving any trace. Many originate in the sun or from distant stars scattered across the galaxy. But some carry an almost unimaginable age, born in the very first second after the Big Bang itself. During that initial instant of cosmic history, neutrinos flooded the expanding universe. Unlike photons, which remain trapped in constant collisions with matter for hundreds of thousands of years, neutrinos slipped free almost immediately because they interact so feebly with everything around them. They have been traveling through space ever since, forming what physicists call the cosmic neutrino background, an invisible sea of ancient particles surrounding us constantly. Though detecting them remains nearly impossible with current technology, they exist everywhere, including inside you at this very moment. Each neutrino represents a relic from the universe's very first heartbeat, still whispering through the cosmos almost 14 billion years after their creation. They are messengers from a time when the universe was newborn, carrying information from an era we can barely comprehend. Astronomers have observed that certain galaxies are not moving in the directions cosmological models would predict. Instead, they appear to be pulled along by some hidden influence lying far beyond the portion of the universe we can observe directly. This mysterious motion has been given the evocative name dark flow. It may be caused by enormous concentrations of mass existing outside our cosmic horizon, regions invisible to our telescopes but powerful enough to bend the trajectories of entire galaxy clusters. We cannot observe these distant regions directly with any instrument we possess, yet we see their fingerprints in the motions of galaxies much closer to us. It serves as a powerful reminder that the observable universe represents merely a patch of something far larger and more complex. Unseen structures beyond our cosmic horizon may still exert their influence on the cosmos we inhabit, shaping the movements of galaxies across vast gulfs of space. When we imagine empty space, we often envision absolute nothingness, a perfect void. But according to quantum theory, even the vacuum is anything but empty or still. Tiny particles constantly blink into existence and vanish again, borrowing energy from the fundamental uncertainty woven into the fabric of reality itself. This restless activity is called the quantum vacuum, and it may hold the key to one of cosmology's greatest puzzles, the nature of dark energy. The accelerating expansion we observe throughout the universe could be driven by the energy inherent in this apparent emptiness. In that sense, every cubic inch of what appears to be nothing is actually alive with quantum possibility, buzzing invisibly with the physics that shapes the ultimate fate of the cosmos. The cosmic microwave background represents the oldest light we can observe, radiation released when the universe was merely hundreds of thousands of years old. To the unaided eye, it appears almost perfectly uniform. Yet sensitive instruments reveal tiny variations within it, delicate ripples measuring less than 1 part in 100,000. These subtle patterns served as the seeds from which galaxies, stars, and planets eventually grew. But some of these ripples appear stranger than others. Certain regions are unusually cold, while others display peculiar alignments that challenge our understanding. These anomalies may represent scars left behind from collisions with other universes, or they might be echoes of exotic energy fields that shaped the inflationary period. The faint patterns etched into this ancient light are not merely random statistical noise. They may be fingerprints of realities far older and vastly larger than our own observable cosmos. Scientists continue studying these anomalous features, searching for clues about what happened before the Big Bang itself. If these patterns do indeed preserve information from pre-Big Bang physics, they would revolutionize our understanding of cosmic origins and the fundamental nature of reality. The ultimate destiny of our cosmos, whether it expands forever, eventually collapses back upon itself, or drifts into thermodynamic equilibrium, depends critically on the nature of its most mysterious components. Dark energy drives the acceleration of expansion. Dark matter provides the gravitational scaffolding shaping galaxies and clusters. Both may be tied to particles that have never been detected in any laboratory. Physicists search tirelessly for these unseen particles using underground detectors shielded from cosmic rays and high-energy particle colliders that smash matter together at tremendous speeds. They hope to glimpse the missing pieces of this cosmic puzzle. If these hypothetical particles exist and can be identified, they will reveal whether our universe is fundamentally stable, whether it may someday decay into a different state, or whether it might even cycle through endless rebirths and deaths. The answers to the cosmos's grandest questions may lie hidden in its smallest constituents. These invisible particles, if discovered, would serve as keys unlocking the story of everything, revealing the ultimate fate awaiting the universe over timescales stretching far beyond human imagination. We experience gravity as a universal force, binding planets to stars and stars to galaxies in cosmic dances. Yet compared to the other fundamental forces governing nature, electromagnetism, and the strong and weak nuclear forces, gravity appears astonishingly feeble. A small refrigerator magnet can lift a paperclip against the gravitational pull of the entire Earth. This weakness has puzzled physicists for decades. Some researchers wonder whether gravity appears weak because it is not actually confined to our familiar three-dimensional space. Instead, it may spread into hidden dimensions that remain invisible to us. If this hypothesis is correct, the gravitational force we experience would represent only a faint echo of a much deeper reality. These extra dimensions might be curled up so tightly that they're too small for us to perceive directly, yet large enough to siphon away most of gravity's strength. This idea may explain why the cosmos holds together in the way it does, and it offers a tantalizing hint that our universe could be part of something more layered and complex than we can currently imagine. When we gaze outward into the night sky, we are truly looking backward through time. Light takes time to travel, so distant objects appear as they were in the past. But there exists a fundamental limit to this backward view, a boundary called the cosmic horizon. Beyond this threshold, light has not had sufficient time to reach us since the Big Bang occurred. Those regions of space are real, filled with galaxies and stars, but they remain forever hidden from our view. The cosmic horizon is not a physical wall or barrier, but rather a limit imposed by perspective, similar to standing on a seashore and seeing only as far as Earth's curve allows. Each year that passes, the horizon grows slightly as light from more distant regions finally completes its journey to us. Yet space itself continues expanding simultaneously, pushing other regions ever farther beyond our observational reach. This cosmic horizon serves as a quiet reminder. No matter how powerful our telescopes become or how far our instruments can peer, there will always be more universe beyond, forever residing outside our sight. It is a humbling acknowledgement of the limits inherent in our cosmic perspective. Most black holes form when massive stars exhaust their fuel and collapse, but there may exist older, stranger varieties, primordial black holes born in the first chaotic moments after the Big Bang. These ancient objects could differ wildly from the black holes we observe today. Some might be incredibly tiny, with event horizons smaller than individual atoms, while others could possess masses rivaling mountains. Over billions of years, the smallest of these primordial black holes would have evaporated completely through a quantum process called Hawking radiation. But others might still drift invisibly through the cosmos today. If they exist in sufficient numbers, they could potentially account for some or even all of the mysterious dark matter that shapes galactic structure. These hidden relics would be scattered throughout space, silent fossils of creation itself. So subtle that a primordial black hole could pass through Earth completely unnoticed, yet so collectively powerful that they may determine the destiny of entire galaxies. Their discovery would link two of cosmology's greatest mysteries in a single elegant explanation. Theories emerging from high-energy physics predict that as the universe cooled from its scorching beginning, strange defects in the fabric of space-time itself could have crystallized into existence. These hypothetical structures are called cosmic strings, infinitely thin yet immensely dense filaments stretching potentially across billions of light years. Unlike ordinary matter or energy, they would represent actual cracks in space-time structure. If two cosmic strings were to intersect and cross paths, they could snap violently, releasing bursts of gravitational waves that would ring through the universe like struck chords resonating across vast distances. Though none have yet been detected despite careful searches, their existence would reveal physics operating far beyond our current understanding. The idea that the early universe might still harbor hidden filaments, invisible to our eyes yet etched permanently into space's fabric, carries both haunting beauty and profound implications. They would be like scars remaining from the cosmos's violent birth, permanent marks left behind by creation itself. Gravitational waves are ripples in the fabric of space-time itself, created by cataclysmic events like colliding black holes or merging neutron stars. But there may also exist far more ancient waves, born during the very first instant of cosmic existence. During the period of cosmic inflation, space-time itself may have shivered with quantum fluctuations. As inflation stretched space exponentially, these microscopic tremors were amplified to cosmic proportions. These primordial gravitational waves would be extraordinarily faint by now, stretched thin by billions of years of expansion. Yet if scientists could detect them, they would serve as direct fossils from the universe's birth, carrying information from the very edge of time itself. Unlike the cosmic microwave background, which only became visible hundreds of thousands of years after the Big Bang, these ripples would transport us back almost to time zero. Researchers search for their subtle signatures in delicate patterns of polarization within the cosmic microwave background radiation. They hope to hear the faintest whispers of creation's first breath, a signal that would revolutionize our understanding of the universe's earliest moments and confirm theories about cosmic inflation. Our Milky Way galaxy, along with numerous others in our cosmic neighborhood, is not simply drifting aimlessly through space. Instead, it is being drawn toward a region hundreds of millions of light years distant called the Great Attractor. This massive gravitational anomaly lies hidden behind dense clouds of dust within the Milky Way itself, making it exceptionally difficult to study directly. Galaxies separated by vast distances all show a shared motion, as though sliding down the slope of some invisible gravitational valley. The true nature of the Great Attractor remains uncertain. It may represent a concentration of galaxy clusters, or it could be something even more massive and complex. Whatever its composition, it exerts gravitational pull strong enough to influence the trajectories of entire galaxies, including our own. We are moving toward it even now, carried along on the slow current of cosmic gravity. This motion has persisted for billions of years and will continue for billions more, a reminder that even galaxies are not stationary but flow through space under the influence of hidden masses. Dark energy represents the mysterious force driving the accelerated expansion of our universe. Currently, it appears to remain constant over time. But what if this changes? Some theoretical models suggest that dark energy could grow stronger over the course of billions of years. If this occurs, the expansion would accelerate more and more dramatically, eventually tearing apart galaxies, then solar systems, then stars, and finally even atoms themselves in a catastrophic event called the Big Rip. In alternative scenarios, dark energy might gradually weaken or fade entirely, allowing gravity to slow the expansion or potentially even reverse it. Because dark energy constitutes the majority of the cosmos's total energy budget, its future behavior will determine absolutely everything about the universe's ultimate fate. And yet, despite its profound importance, we do not currently know whether dark energy remains constant or evolves with time. The entire destiny of the universe may rest upon the hidden nature of this invisible force permeating all of space. Between the luminous filaments of the cosmic web lie immense empty regions known as voids. These vast expanses can span hundreds of millions of light years yet contain only a handful of scattered galaxies. Voids are not static pools of emptiness. However, they are actively expanding faster than the rest of the universe as matter continues flowing outward toward denser regions along the web's glowing threads. In a sense, these are the growing hollows of the cosmos, ballooning steadily as galaxies drift away from their centers. By studying these voids carefully, scientists can test fundamental theories about the nature of dark energy and the mechanics of cosmic expansion. For now, they remain among the quietest and loneliest regions in all of existence, vast oceans of near-nothingness, still stretching wider with each passing moment. Their emptiness is profound, yet they play a crucial role in the cosmic structure. The voids and filaments together create the large-scale architecture of the universe, a pattern that emerges from the interplay of gravity and dark energy across billions of years. When we envision the universe, we often picture it as geometrically flat, stretching endlessly in all directions without curvature. But cosmological geometry is more subtle than this simple picture suggests. Depending on its total energy content, the universe could possess positive curvature like the surface of a sphere, or negative curvature resembling a saddle shape. Current observations indicate that the universe is astonishingly close to being perfectly flat, so close that if any curvature exists at all, it remains too small to detect with certainty using our best instruments. A universe with even the tiniest degree of curvature would, over unimaginable distances, bend the paths of light rays in ways that reveal its overall shape. For now, we inhabit a cosmos that appears flat to all our measurements. Yet cosmologists continue their search for that faint hidden curve, because discovering it would tell us profound truths about the universe's ultimate size, its topology, and its long-term fate stretching into the distant future. The cosmic microwave background, the afterglow of the Big Bang itself, appears mostly smooth and uniform when mapped across the entire sky. Yet scattered throughout this ancient light are unusual features, including patches that appear colder than expected based on theoretical predictions. One of the largest anomalies is known simply as the cold spot, a region where the temperature of this primordial radiation dips strangely low. Some researchers suggest it may be caused by an enormous void lying in that direction, draining energy from photons as they traverse this empty region. Others propose more exotic explanations, including the possibility that it represents a fingerprint of physics operating beyond our observable universe, perhaps even the scar left by a collision with another cosmic bubble. Whatever its origin, the cold spot remains one of the most puzzling anomalies written into the universe's oldest visible light. It challenges our assumptions about cosmic uniformity and keeps cosmologists searching for deeper explanations hidden in this ancient glow. In the period following the Big Bang, the universe initially existed in darkness. Then hydrogen and helium began gravitationally gathering into the very first stars. These primordial objects were fundamentally different from any stars we observe today. With no heavier elements available to cool the collapsing gas efficiently, these stars grew enormous, hundreds of times more massive than our Sun. Their light blazed intensely, shining white-blue across the void. They lived fast, burning through their nuclear fuel at prodigious rates. In only a few million years, these population 3 stars forged the very first heavier elements, carbon, oxygen, iron, deep within their cores. When they died, they scattered these newly created elements across space, seeding the raw material that would later form subsequent generations of stars, planets, and eventually life itself. Though none of these first stars remain today, every carbon atom in your body may have been born inside one of these long-vanished giants. They were the universe's first alchemists, transforming primordial hydrogen into the diverse elements that make complex chemistry possible. The most massive among these first stars ended their brief lives in gravitational collapse. Their gravity was so overpowering that when their nuclear fuel was exhausted, no force could prevent them from imploding. Some exploded as supernovae, leaving behind neutron stars, while others collapsed directly into black holes without any explosive fanfare. These black holes were unique, not the remnants of ordinary stars from later cosmic eras, but the direct descendants of the first cosmic fires. They may have served as seeds, growing gradually over billions of years into the supermassive black holes that now anchor the centers of galaxies. If this scenario is correct, the brilliant quasars we observe at the edge of the observable universe, powered by black holes billions of times the Sun's mass, may trace their lineage directly back to those first collapsing stars born at the dawn of cosmic time. This connection between the first stars and the largest black holes in existence today represents one of the most elegant narratives in cosmic history. Though the night sky appears motionless to our eyes, our galaxy pursues a ceaseless journey through space. The Milky Way, along with all its stars, planets, and nebulae, drifts through the cosmic web at speeds exceeding 1 million miles per hour. This motion results partly from gravitational pulls exerted by nearby galaxies and massive clusters, and partly from vast unseen structures lying beyond. To us, this tremendous velocity feels invisible because everything around us moves together as a unified whole. But when astronomers carefully measure the cosmic microwave background, they can detect a faint dipole pattern, a subtle distortion caused by a galaxy's motion through space. It serves as a reminder that there is no absolute state of rest anywhere in the universe. Everything drifts, everything flows, carried along in the great cosmic current that has been running since the beginning of time. Galaxies do not exist in isolation across the cosmos. They gather together into clusters, and those clusters themselves assemble into even larger structures called superclusters. These superclusters stretch for hundreds of millions of light years, linked together by filaments of galaxies and separated by vast cosmic voids. Together, they form what astronomers call the cosmic web, a pattern remarkably resembling spider silk strands or the branching filaments of neurons in a brain. Our own Milky Way resides within the Laniakea supercluster, a sprawling region containing hundreds of thousands of individual galaxies. When scientists map these enormous structures, what emerges is not chaos or randomness, but elegance and order. Gravity has been sculpting luminous threads across the universe for billions of years, revealing a hidden architectural pattern that spans distances almost beyond comprehension. This cosmic web represents the largest known structure in the universe, and its existence demonstrates how matter organizes itself on the grandest possible scales. Quasars are among the most luminous beacons in the universe, galaxies whose central supermassive black holes feed so voraciously on surrounding matter that they blaze brighter than all their stars combined. Some quasars we observe today emitted their light less than 1 billion years after the Big Bang, when the cosmos was still in its infancy. To shine so brilliantly so soon after creation, their central black holes must have grown with astonishing speed, reaching masses of 1 billion suns in just a fraction of cosmic history. These ancient quasars act like lighthouses, illuminating the fog of intergalactic gas and helping us peer back into the reionization era, the epoch when the first galaxies carved channels of light through the primordial darkness. Their existence poses profound questions that cosmologists are still working to answer. How did black holes grow so massive so quickly? What seeds gave rise to them in the early universe? The answers may reshape our understanding of galaxy formation and black hole evolution. Astronomers mapping the distribution of interstellar gas have discovered that our Sun lies within a vast cavity carved into the galaxy's structure, a bubble stretching hundreds of light-years across. This region, called the local bubble, is unusually empty compared to its surroundings. It was likely created by a chain of supernova explosions that occurred millions of years ago, which blew away the surrounding material like wind-clearing fog. Today, our Sun and its neighboring stars drift quietly within this rarefied zone, bathed in the faint glow of hot plasma. The edges of the bubble form denser walls composed of gas and dust where new stars are currently being born. The thought that our solar system resides inside the lingering footprint of ancient stellar deaths adds a strange intimacy to our place in the cosmos. We live within the aftermath of stellar violence, in a bubble carved by stars that exploded long before Earth existed, a reminder that even our local cosmic neighborhood carries the scars of dramatic events from the distant past. When astronomers simulate the growth and evolution of cosmic structure, they discover that ordinary matter alone cannot produce the patterns we observe throughout the universe. Something unseen, dark matter, must weave an invisible scaffolding beneath it all, guiding the distribution of visible matter into the shapes we recognize. In these computer simulations, dark matter clumps into vast filaments stretching across space, creating a hidden network that guides the flow of galaxies into strands and nodes. Our own Milky Way sits embedded within one of these invisible filaments, like a dewdrop caught on a spider's thread. We cannot see this dark matter directly through any telescope or instrument, but we observe its gravitational influence sculpting the grand architecture of the universe. Without this hidden scaffolding, galaxies would fly apart under their own rotation, and the cosmic web would unravel into scattered fragments drifting alone through the void. Dark matter represents the hidden foundation upon which all visible cosmic structure rests, an invisible framework holding the universe together. The true identity of dark matter remains one of cosmology's greatest unsolved mysteries. Invisible and undetectable except through gravitational effects, it pervades the universe. One intriguing candidate is the action, a hypothetical particle predicted by certain quantum physics theories. Unlike the heavy particles once imagined to explain dark matter, actions would be incredibly light, possessing less mass even than neutrinos, yet produced in such enormous quantities that together they could outweigh all visible matter in the cosmos. Actions would interact so weakly with ordinary matter that they slip through stars, planets, and even the most sensitive detectors without leaving a trace. Scientists have constructed experiments using ultrasensitive magnetic fields and resonant cavities, hoping to catch even the faintest whisper of these elusive particles. If discovered, actions would not only solve the dark matter mystery but also forge connections between cosmology and deep questions in particle physics. Their detection would represent one of the most profound discoveries in the history of science, revealing the invisible substance that dominates the universe's mass. Some versions of inflationary theory predict that our observable universe represents only one bubble in an endless multiverse, a vast collection of separate cosmic domains. If this is true, the fundamental laws of physics governing each bubble might vary from one to another. In one universe, stars might never form because gravity operates too weakly. In another, atoms themselves might not exist due to different force strengths. Our own universe appears finely tuned, with its physical constants balanced in precisely the way necessary to allow galaxies, complex chemistry, and ultimately life to emerge. This raises a haunting possibility. Perhaps we inhabit one universe among countless others, most sterile and lifeless, some chaotic and unstable, but ours balanced just delicately enough for complexity to bloom. Though we cannot observe beyond our cosmic horizon to verify this idea, it invites us to wonder at the fragile and perhaps improbable conditions that make our existence possible here and now. In the theory of eternal inflation, the universe does not expand as a single isolated bubble, but rather as an endless froth of cosmic domains. Regions of space stop inflating and settle down to form universes like ours, while other regions continue expanding forever, perpetually spawning new bubbles in an infinite cascade. Each bubble could be infinite in size by itself, and together they form a multiverse without any ultimate boundary or edge. In this extraordinary picture, the Big Bang was not the beginning of everything. It was simply the birth of our local cosmic region. Other universes may lie forever beyond our reach, each possessing its own physics, its own galaxies and stars, and perhaps its own forms of life completely alien to anything we could imagine. It represents a vision of reality so vast that even our observable cosmos, containing its 2 trillion galaxies, would be merely one small ripple on an endless cosmic sea, a single moment in an eternal story with no beginning and no end. For the first few 100,000 years following the Big Bang, the universe existed as an opaque fog composed of free particles. Electrons and protons drifted separately, constantly scattering photons so completely that light could not travel more than a tiny distance before being deflected. The cosmos was a glowing plasma, luminous but opaque, with no clear paths for radiation to follow. Then, as the universe expanded and cooled below a critical temperature, electrons settled into stable orbits around protons, forming the first neutral hydrogen atoms. Suddenly, photons were liberated, able to fly unhindered across space for the first time. In that instant, the universe transformed from opaque to transparent, and the light we now call the cosmic microwave background began its epic journey across billions of years. Every time we measure that ancient glow today, We are witnessing the precise moment when the universe first allowed light to travel freely, a timeless afterimage of a cosmos lifting its primordial veil and becoming transparent to radiation. After the initial recombination event made the universe transparent, it became dark once again, filled with neutral hydrogen gas but lacking any sources of light. For hundreds of millions of years, there were no stars to illuminate space. Then gradually, the first galaxies began to ignite. Their newborn stars and active quasars flooded space with intense ultraviolet radiation powerful enough to ionize hydrogen atoms once more, breaking them back into free protons and electrons. This epoch is called the reionization era, a time when the fog lifted not through cooling this time, but by being pierced and burned away by starlight. Reionization carved expanding bubbles of transparency around the first galaxies, gradually merging until the entire universe became illuminated from within. When we observe distant galaxies and quasars today, we are catching glimpses of that transformative moment when cosmic darkness finally gave way to the dawn of light, and the universe became permanently illuminated by its own stellar furnaces. We know about the cosmic microwave background, the light released when the universe became transparent to photons. But before that pivotal moment, another background formed, a vast sea of neutrinos released only seconds after the Big Bang itself. These ghostly particles still stream through space today, forming what physicists call the cosmic neutrino background. Unlike photons, which remain trapped in constant collisions with matter for hundreds of thousands of years, neutrinos escaped almost immediately, carrying with them information from the universe's earliest heartbeat. Yet because they interact so weakly with ordinary matter, we have never directly detected this ancient neutrino sea. These particles flow through planets, stars, and our bodies almost without leaving any trace whatsoever. Instruments sensitive enough to catch even a faint echo of this background are still being designed and dreamed of by physicists. If one day we successfully detect the cosmic neutrino background, it would be like opening a hidden window into the very first second of existence itself, a direct connection to an era even more ancient than the cosmic microwave background reveals. Cosmic rays are high-energy particles that continuously rain down upon Earth, striking our atmosphere with invisible impacts. Most originate from sources within our own galaxy, such as exploding supernovae. But some cosmic rays carry energies so extreme that no known astrophysical event in the Milky Way could possibly have launched them to such tremendous speeds. These ultra-high-energy cosmic rays may originate from far beyond our galaxy, perhaps from the powerful jets launched by distant quasars, or from violent collisions between entire galaxy clusters. Each particle has traveled for millions or even billions of years through intergalactic space until, by pure chance, it encounters Earth's atmosphere. When such a particle strikes, it unleashes a cascade of secondary particles, momentary fireworks of invisible cosmic origin. Even now, despite decades of research, we don't fully understand what accelerates the most powerful particles in the universe to such incredible energies. We know only that they come from somewhere far beyond our home galaxy, carrying energy from the cosmos's most violent events. Black holes are not always solitary objects drifting alone through space. In galaxies where stars crowd densely together and stellar clusters interact gravitationally, black holes can be drawn into binary pairs. Over enormous spans of time, they spiral gradually closer. radiating away energy in the form of gravitational waves until they finally merge into a single, larger black hole. Each collision creates a tremendous burst of space-time ripples that propagate outward across the universe. Over billions of years, these mergers may gradually grow the black holes residing at the centers of galaxies to enormous sizes. When such mergers occur, the energy released can dramatically alter the flow of surrounding gas, shaping patterns of star formation and influencing the overall structure and evolution of the host galaxy. In this way, black hole mergers are not merely rare cosmic fireworks to be observed and admired. They are part of the quiet, ongoing architecture of the cosmos itself, gradually sculpting galaxies into the diverse shapes and forms we observe throughout the universe today. Einstein predicted their existence more than a century ago, and after decades of technological development, we finally heard them. Gravitational waves are ripples in the fabric of space-time itself, created when massive objects like black holes or neutron stars collide with tremendous violence. They stretch and compress space as they pass through it, though only by distances less than the width of a single proton, impossibly tiny distortions that require extraordinarily sensitive instruments to detect. With detectors like LIGO and Virgo, scientists have now recorded dozens of these events, distant cataclysms occurring billions of light years away, their whispers reaching us across cosmic time. Each gravitational wave carries a unique signature, revealing information about the masses, sizes, and orbital dynamics of the objects that created it through their final violent dance. And someday, if technology advances enough to hear even fainter signals, we may detect the background hum of gravitational waves from the earliest universe itself, echoes of creation still rolling through space-time, carrying messages from the moment of the Big Bang. The universe does not expand at a constant, unchanging pace. During its first fractions of a second, cosmic inflation drove an almost unimaginable expansion. Space stretched faster than light itself could travel. After inflation ended, gravity began slowing things down as matter exerted its attractive pull against the outward flow. For billions of years, galaxies drifted apart at a gentle, gradually decelerating rate. But approximately 5 billion years ago, something changed. The expansion began speeding up again, driven by the mysterious influence of dark energy. This shifting pace reveals that the cosmos has passed through distinct phases, each governed by the changing balance of forces and energies within it. From rapid inflation to slow deceleration to the present acceleration, the rhythm of cosmic expansion resembles a heartbeat that changes with time, still unfolding into an unknown future whose ultimate fate depends on the nature of dark energy itself. Ordinary stars form when clouds of gas collapse under their own gravity, igniting nuclear fusion in their cores. But some theories propose a stranger origin story for hypothetical objects called dark stars. In the very early universe, dark matter may have clumped together densely enough that its annihilation released bursts of energy into the surrounding gas. Instead of collapsing completely to form black holes, these clumps could have inflated into giant dark stars, bizarre objects powered not by nuclear fusion, but by dark matter itself. They would have been enormous, glowing faintly with heat generated from within by ongoing dark matter annihilation. Unlike ordinary stars, their light would have been nearly invisible to us, radiating primarily in infrared wavelengths. If such stars existed, they could have been the first luminous beacons in the cosmos, later collapsing into black holes that served as seeds for the supermassive giants anchoring galaxies today. Though still hypothetical, the idea of stars born from the invisible matter dominating the universe offers a haunting glimpse of what might once have existed in the cosmic dawn. When we carefully map the cosmic microwave background, the afterglow of the Big Bang, we find that it is almost perfectly uniform across the entire sky. Almost, but not entirely. There exists a slight asymmetry, a subtle lopsidedness where one hemisphere of the sky displays slightly stronger temperature fluctuations than the opposite hemisphere. This imbalance puzzles cosmologists because the early universe should have been nearly identical in every direction, with no preferred orientation or axis. Some researchers suggest this asymmetry might simply be a statistical quirk, random chance manifesting in our particular cosmic patch. Others propose deeper explanations, such as hidden physics from the inflationary period or even interactions with regions lying beyond our observable universe. Though subtle and easily overlooked, this lopsidedness challenges our fundamental assumption that the cosmos is perfectly isotropic, the same in all directions. It keeps cosmologists searching for the hidden story written into this ancient light, wondering whether it points toward new physics or simply represents cosmic coincidence. Among the complex patterns visible in the cosmic microwave background, scientists have noticed something genuinely unusual. Large-scale features appear to align along a common axis across the sky, an orientation that shouldn't exist if the universe were truly random and uniform at the larger scales. This unexpected alignment has been playfully nicknamed the axis of evil, though the mystery it represents is entirely serious. Even more puzzling, some of the largest structures in the universe, galaxy superclusters and cosmic filaments, seem to follow this same mysterious orientation. Whether this represents mere coincidence, a statistical fluke that will disappear with better data, or a sign of previously unknown physics, no one can say with certainty. The name may be lighthearted, but the question it raises is profound. Why should the universe, so vast and ancient and seemingly random, show any preference whatsoever for a particular direction in space? The axis of evil remains one of cosmology's most intriguing unsolved puzzles. The universe exists balanced on what seems like an impossibly narrow edge. The strength of gravity, the mass of fundamental particles, the charge of electrons. If any of these values were altered even slightly, the cosmos would look radically different from what we observe. Stars might never ignite if nuclear forces were weaker. Atoms might never form if electromagnetic forces had different strengths. Galaxies might collapse too rapidly or disperse too quickly to allow complex structures. This delicate balance is known as fine-tuning, and it has fascinated cosmologists for decades because the precision required seems almost impossibly exact. Some researchers see it as a deep mystery requiring explanation through more fundamental laws of physics we have yet to discover. Others point to the multiverse hypothesis. If countless universes exist with randomly varying constants, we naturally find ourselves in one where conditions happen to permit observers to exist. Whatever the true explanation, it remains humbling to realize that the entire visible universe, from the largest galaxy cluster to the oxygen in your breath, depends on the delicate tuning of invisible constants woven into the very fabric of reality itself. It sounds like pure science fiction, yet the holographic principle represents a serious idea in theoretical physics, actively researched by leading scientists. It suggests that everything in our universe, stars, galaxies, planets, even ourselves, might be described not in three spatial dimensions, but by information encoded on a distant two-dimensional surface, similar to how a flat hologram contains the illusion of depth. Just as a holographic image creates three-dimensional appearance from two-dimensional data, the cosmos we experience might emerge from information written on some cosmic boundary. This strange idea originated from studying black holes, where researchers discovered that information appears to be stored on the event horizon, the two-dimensional surface, rather than within the three-dimensional interior. If this principle applies to black holes, it might apply to the entire universe as well. The holographic principle doesn't suggest that reality is an illusion or simulation, but rather that space and time themselves may be emergent phenomena, shadows cast by a deeper, more fundamental layer of physics operating in fewer dimensions than we perceive. At the smallest scales of existence, quantum physics governs everything. Particles flicker in and out of existence, and uncertainty is fundamental law rather than limitation. During cosmic inflation, these tiny quantum fluctuations were stretched to astronomical scales, becoming slight variations in the density of matter spread across the expanding universe. Over billions of years, gravity amplified these subtle ripples, drawing matter preferentially into some regions rather than others. From those microscopic quantum seeds grew galaxies, stars, planetary systems, and eventually life itself. It is astonishing to contemplate that everything visible in the night sky, from our Milky Way to the most distant galaxy cluster observable, may have originated from microscopic quantum jitter, amplified by the vast machinery of cosmic expansion. The entire universe, in a very real sense, rests upon the chance tremors of the quantum realm, tiny fluctuations magnified across time and space into the grand cosmic structures we observe today. Cosmic inflation proposes that the universe expanded faster than light during its first instant, but some theoretical versions suggest this process didn't occur uniformly everywhere. While our particular region slowed down and became the universe we inhabit, other regions may have continued inflating indefinitely, forming completely separate universes in an endless process. This might happen perpetually, with baby universes budding off like bubbles rising in boiling water. Each new universe would be sealed off from all the others by expansion faster than any signal, even light itself, could traverse. Some of these bubble universes might follow laws of physics radically different from ours, while others might closely resemble our own cosmos with similar galaxies and stars. If this theory is correct, our observable universe represents just one blossom on an infinite cosmic tree, its countless branches forever hidden from one another, each carrying its own unique version of physical reality. We would be fundamentally unable to observe or interact with these sibling universes, yet they might exist nonetheless in endless profusion. The number of galaxies in the observable universe stretches almost beyond human comprehension. Early astronomical estimates suggested hundreds of billions, which already seems staggering. But deep-field images captured by telescopes like Hubble, peering into tiny patches of seemingly empty sky, revealed far more structure than anyone anticipated. Counting carefully across these deep surveys, cosmologists now estimate there may be approximately 2 trillion galaxies within the observable universe. To provide perspective on this number, If you somehow collected all the sand grains from every beach and desert on Earth, every particle from the Sahara to the shores of Australia, the total would still fall short of the number of galaxies above us. Each of those 2 trillion galaxies contains billions or even trillions of individual stars, and each star could potentially host its own system of planets, moons, and perhaps life. The scale becomes so immense that even the concept of infinity feels close at hand. When we gaze upward at the night sky, we perceive only the faintest sprinkling of this cosmic ocean, a handful of nearby sparks scattered among an overwhelming abundance that stretches to the limits of observation and beyond. In most regions of the universe, energy manifests as positive, tied to matter, radiation, and motion. But quantum field theory predicts scenarios where the energy density of space itself could dip below zero, creating exotic regions of negative energy. These unusual states are not simply ordinary emptiness or vacuum, but something fundamentally different that could warp space-time in unexpected ways. Negative energy might potentially enable exotic phenomena like traversable wormholes or even stable warp bubbles that could theoretically allow faster-than-light travel without violating relativity. Though still deeply theoretical, negative energy has been glimpsed in tiny quantum effects such as the Casimir force, a measurable attraction between closely spaced metal plates in a vacuum caused by subtle quantum fluctuations. If negative energy can exist on small scales in laboratory conditions, perhaps it might also manifest in larger cosmic contexts. Negative energy density could represent one of the strangest hidden features of the universe, rare and fleeting, yet profound enough to reshape our understanding of what emptiness and nothingness truly mean at the deepest levels of physics. Dark matter remains one of cosmology's greatest enduring mysteries, invisible and undetectable through any means except its gravitational influence on visible matter. One intriguing possibility is that dark matter consists not of exotic particles at all, but of black holes formed during the first moments after the Big Bang. These primordial black holes could range enormously in size, from objects as small as asteroids to masses comparable to stars, scattered throughout the cosmos. Unlike ordinary black holes that form from collapsing stars, primordial black holes would be fossils preserving conditions from the universe's earliest fluctuations. If enough of them exist, distributed throughout space, they could potentially account for all the dark matter we observe shaping galaxies and clusters through gravitational effects. Detecting them would not be straightforward. They could drift invisibly through intergalactic space, revealing themselves only through rare gravitational lensing effects when they pass between us and distant light sources. If confirmed, primordial black holes would elegantly tie together 2 of the universe's greatest mysteries in a single comprehensive explanation. Photons, the fundamental particles carrying light, are described by quantum wave functions. In principle, a single photon's wave can extend indefinitely, stretching across vast distances without limit. In our expanding universe, light from the earliest epochs has been redshifted to progressively longer and longer wavelengths as space itself stretches. Some photons from the cosmic microwave background now possess wavelengths measured in millimeters, small by everyday standards, but not infinitesimally tiny. Yet in theory, a photon could be stretched so thin that its quantum wave function spans the entire observable universe. This represents something we cannot observe directly, but it reveals how strange and counterintuitive quantum mechanics becomes when applied to cosmic scales. Even a single particle of light might not be truly local in any conventional sense, but rather universal, its wave function rippling silently across billions of light years, existing simultaneously throughout vast regions of space. This quantum behavior at astronomical scales challenges our intuitions about particles and waves, suggesting that the boundary between them blurs at the largest distances. Entropy represents the universal tendency for systems to progress from order toward disorder. On Earth, we observe this as energy dispersing and structures breaking down over time. At the cosmic scale, entropy ensures that stars will eventually exhaust their fuel, galaxies will drift apart beyond mutual gravitational reach, and all usable energy will gradually dissipate into uniformity. In the far future, trillions upon trillions of years from now, the universe may reach what physicists call heat death, a state where everything has cooled to near uniformity and no energy gradients remain to drive any change whatsoever. It would not be a fiery ending or dramatic collapse, but rather a slow fade into cold, dark stillness where nothing can happen anymore because no differences exist to enable processes. This ultimate fate represents the quiet triumph of entropy, the cosmos gradually winding down like a clock running out of energy, until all becomes still, dark, and unchanging for eternity. It is a sobering reminder that even the grandest structures and most energetic processes must eventually yield to the relentless march of thermodynamics. The fabric of space-time itself might not be stable permanently. Quantum field theory suggests that our universe could exist in what's called a false vacuum, a seemingly stable state that is not actually the lowest energy configuration possible. Like a ball balanced precariously in a shallow valley with a deeper valley nearby, the universe might someday spontaneously tunnel into a lower energy state. If this vacuum decay occurs, it would unleash a bubble of true vacuum expanding at the speed of light, rewriting the laws of physics everywhere it touches. Inside the bubble, fundamental constants would shift, particles might gain different masses, and the chemistry enabling stars, planets, and life would cease to function. The bubble would be utterly unstoppable, eventually consuming all of space. This possibility remains purely theoretical, and if it happens, it likely won't occur for an incomprehensibly long time, if ever. But the fact that it represents even a remote possibility reminds us that the universe's apparent stability might be temporary on the longest timescales imaginable. Beyond the farthest reaches visible to our most powerful telescopes lies a boundary we can never cross, not because of technological limitations, but due to the fundamental nature of spacetime itself. The observable universe has a finite edge, not a physical barrier, but simply the distance light has been able to travel since the Big Bang occurred approximately 13.8 billion years ago. Beyond this cosmic horizon exist regions of space that are real, filled with galaxies and stars, but from which light has not yet had time to reach us. As the universe continues aging, this horizon gradually expands as light from increasingly distant regions completes its journey. Yet paradoxically, space itself also expands, pushing the most distant regions away faster than light can travel toward us. This means that some galaxies currently within our observable universe will eventually drift beyond the cosmic horizon, disappearing from view permanently. No matter how advanced our technology becomes, we will never observe what lies beyond this fundamental boundary. It represents an absolute limit imposed by the cosmos itself on what we can ever know about the full extent of reality. Cosmic rays continuously bombard Earth's atmosphere, high-energy particles arriving from space and creating cascades of secondary particles when they strike air molecules. Most originate from energetic events within our galaxy, such as supernova explosions. However, some cosmic rays arrive carrying energies so extreme that they challenge our understanding of astrophysical acceleration mechanisms. These ultra-high-energy cosmic rays possess energies millions of times greater than anything we can produce in our most powerful particle accelerators. The sources capable of accelerating particles to such tremendous speeds remain uncertain. Perhaps the relativistic jets launched by supermassive black holes in distant quasar cores, or shock waves from collisions between entire galaxy clusters. Each of these extraordinary particles has traveled for millions or billions of years across intergalactic space, carrying energy from the universe's most violent and powerful events, until by pure chance it intersects Earth's atmosphere and announces its arrival through a brief shower of secondary particles. When galaxies collide, a slow-motion cosmic catastrophe unfolding over hundreds of millions of years, their constituent stars rarely actually strike one another due to the vast spaces between them. However, their gravitational interactions can be dramatic, flinging stars into new orbits and triggering intense bursts of star formation as gas clouds are compressed. These galactic mergers have shaped cosmic structure throughout history. Our own Milky Way has absorbed numerous smaller galaxies over billions of years, and it is currently on a collision course with the Andromeda Galaxy. In approximately 4 billion years, the two will begin merging into a single, larger elliptical galaxy. During such mergers, the supermassive black holes at each galaxy center will eventually spiral together and merge, releasing tremendous gravitational waves. The merger process fundamentally reshapes both galaxies involved, redistributing stars and gas in ways that can either trigger new star formation or quench it entirely by heating gas too much for it to collapse. The existence of dark matter is supported by overwhelming gravitational evidence accumulated over decades of astronomical observation. Galaxies rotate at speeds that would fling them apart if only visible matter provided gravitational binding. Galaxy clusters contain far more mass than their visible stars and gas can account for. Gravitational lensing, the bending of light around massive objects, reveals invisible mass distributions throughout the universe. All these independent lines of evidence point toward the same conclusion. Approximately 85% of the universe's matter is completely invisible to our telescopes, interacting only through gravity. This dark matter outweighs all visible matter by a factor of 5 to 1, making it the dominant form of mass in the cosmos. Yet despite its abundance and importance, we still don't know what dark matter actually is. Decades of increasingly sensitive experiments have searched for dark matter particles without definitive detection. This missing piece of cosmic composition remains one of physics' most pressing unsolved problems, with profound implications for our understanding of the universe's structure and evolution. Wormholes are theoretical shortcuts through space-time, tunnels connecting distant regions of the universe or even separate universes entirely. Einstein's general relativity permits their existence mathematically, though whether they can actually form and remain stable is deeply uncertain. If traversable wormholes could exist, they would revolutionize our understanding of space and time, potentially allowing instantaneous travel between distant locations. However, maintaining a stable, traversable wormhole would likely require exotic matter with negative energy density, something that may exist only in tiny quantum fluctuations, if at all. Without this exotic matter, wormholes would collapse instantly, pinching off before anything could pass through them. The possibility of wormholes connects to some of physics' deepest questions about the nature of space-time, quantum mechanics, and gravity. While they remain firmly in the realm of speculation and theoretical physics, their mathematical possibility within general relativity keeps researchers exploring whether the universe might permit such extraordinary structures. Strikingly, the large-scale structure of the universe, with its filaments and nodes of galaxies connected by the cosmic web, bears remarkable resemblance to neural networks in biological brains. Both consist of nodes connected by filamentous pathways, with most space occupied by emptiness. The similarity is visually striking when comparing maps of cosmic structure with images of neurons. This resemblance is likely coincidental rather than indicating any deeper connection, but it illustrates how certain organizing principles, driven by networks of interactions and flows of energy or information, can create similar patterns across vastly different scales and contexts. Some researchers have explored whether this similarity might hint at fundamental organizational principles operating across nature at multiple scales. While speculative, these comparisons remind us that the universe displays patterns and structures that sometimes echo across different domains in unexpected ways, from the microscopic to the cosmic. Time is not absolute, but relative, flowing at different rates depending on velocity and gravity, as Einstein's theories revealed. Near massive objects, time runs slower than in empty space. For objects moving at high speeds, time dilates relative to stationary observers. These effects are small in everyday experience but become dramatic in extreme conditions. Near a black hole's event horizon, time slows so dramatically that an outside observer would see infalling objects appear to freeze in place, taking infinite time to actually cross the horizon. For the falling object itself, however, time passes normally. It crosses the horizon in finite time and plunges toward the singularity. This relativity of time means that simultaneity itself is not absolute. Events that appear simultaneous to one observer may occur in sequence to another. The universe has no universal clock ticking uniformly everywhere. Time is woven into the fabric of space-time itself, flexible and dependent on conditions. At the smallest conceivable scales of space and time, known as the Planck scale, our current theories of physics break down completely. The Planck length, approximately 10 to the negative 35 meters, and the Planck time, about 10 to the negative 44 seconds, represent limits beyond which quantum fluctuations of space-time itself become dominant. At these scales, the smooth fabric of space-time may dissolve into a quantum foam where space and time themselves fluctuate wildly and unpredictably. Our current theories, general relativity and quantum mechanics, cannot describe this regime because they become mathematically incompatible at these extremes. Understanding physics at the Planck scale would require a complete theory of quantum gravity, which remains one of physics' greatest unsolved challenges. String theory, loop quantum gravity, and other approaches attempt to bridge this gap, but experimental verification remains impossibly difficult because the Planck scale lies far beyond our ability to probe directly. Some cosmological models propose that the universe undergoes endless cycles of expansion and contraction rather than having a single unique beginning. In these cyclic universe models, each Big Bang is not a true origin but rather a transition from a previous collapsed state, a cosmic bounce rather than an absolute beginning. In such scenarios, the universe might contract into a big crunch, but instead of collapsing to a singularity, quantum effects could trigger a bounce, launching a new expansion phase. This cycle could repeat infinitely, with each cycle potentially lasting trillions of years before contracting and rebounding again. These models attempt to avoid the conceptual difficulties of a true beginning of time, replacing it with an eternal cycling process. While speculative and lacking definitive observational evidence, they represent attempts to understand cosmic origins without requiring an absolute start point to existence itself. The cosmic microwave background represents the oldest electromagnetic radiation we can observe, a snapshot of the universe when it was only 380,000 years old. Before this moment, the universe was opaque to light. After this recombination epoch, photons streamed freely through transparent space. This ancient glow has traveled through expanding space for over 13 billion years, cooling and stretching in wavelength from visible light to microwaves. It arrives at Earth from all directions equally, creating a nearly uniform background radiation that fills the entire sky. Tiny temperature variations in this background, differences of only a few millionths of a degree, reveal the density fluctuations that eventually grew into galaxies and clusters. By studying these patterns in exquisite detail, cosmologists can test theories about the universe's composition, age, geometry, and evolution with remarkable precision. Some physicists propose that if our universe's vacuum eventually decays into a lower energy state, the bubble of new vacuum wouldn't necessarily destroy everything. It might instead create conditions for a new universe to emerge with different physical laws. In this speculative scenario, our universe could give birth to offspring universes through vacuum decay events. Each daughter universe would be causally disconnected from its parent, potentially developing entirely different constants, particles, and forces. Life and structure as we know them would be impossible in most such universes, but some might permit new forms of complexity to emerge. This idea extends the multiverse concept in a different direction, not just bubble universes from eternal inflation, but generations of universes spawned through vacuum decay, each potentially spawning its own descendants in an infinite tree of cosmic evolution. Throughout cosmic history, the balance of forces shaping the universe's expansion has shifted. In the earliest moments, radiation dominated, filling space with intense energy. As the universe expanded and cooled, matter became dominant, with its gravity gradually slowing expansion. Most recently, dark energy has become dominant, driving accelerated expansion that will likely continue indefinitely. These transitions represent major phase changes in cosmic evolution, each characterized by different dynamics governing how space expands and how structures form. Understanding these eras helps cosmologists piece together the universe's complete history from its first instant through to its ultimate fate. Each era left distinctive signatures in cosmic structure and radiation that we can still detect today, allowing us to reconstruct this epic history. The Big Bang itself remains shrouded in mystery, not just what happened during it, but what, if anything, came before. Some theories propose that time itself began at the Big Bang, making the question of before meaningless. Others suggest that our Big Bang emerged from a previous state, perhaps a contracting universe that bounced, or a quantum fluctuation in some pre-existing background. The extreme conditions at the Big Bang, infinite density and temperature in classical models, indicate that our current physical theories break down at this boundary. General relativity predicts a singularity where its own equations cease to be valid, suggesting that a more complete theory incorporating quantum effects is necessary to understand the true beginning. What we call the Big Bang may not have been the absolute origin of existence, but rather a transformation or phase transition from something else entirely. Until we develop a working theory of quantum gravity capable of describing such extreme conditions, the ultimate origin will remain one of physics' deepest mysteries. The accelerating expansion of the universe, driven by dark energy, means that galaxies beyond our local gravitational group are receding from us at ever-increasing speeds. Eventually, they will cross the cosmic horizon and disappear from view forever. In the far future, trillions of years from now, astronomers in the Milky Way would observe only their local galaxy cluster, with all other galaxies having receded beyond the observable horizon. The cosmic microwave background would cool and redshift into invisibility. The evidence we currently have for the Big Bang and cosmic expansion would gradually disappear. Future civilizations, if any exist, would inhabit a universe that appears static and lonely, containing only their local island of galaxies surrounded by emptiness. This perspective highlights how cosmology depends on our particular moment in cosmic history. We are fortunate to exist when the universe still reveals its origins and evolution. In the deep future, this knowledge would become almost impossible to obtain through direct observation. Light itself has limits, imposed by the finite speed at which it travels through space. Even though light moves at the universe's ultimate speed limit, approximately 300,000 kilometers per second, the vast distances between cosmic objects mean that light takes enormous time to traverse them. When we observe distant galaxies, we see them not as they are now, but as they were when their light began its journey toward us. Looking at a galaxy 1 billion light-years away, we see it as it existed 1 billion years ago. The most distant galaxies we can observe appear as they were over 13 billion years ago, less than a billion years after the Big Bang. This means astronomy is fundamentally a study of history. We cannot see the present state of distant objects, only their ancient past, preserved in the light that has traveled across cosmic time to reach our telescopes tonight. Dark energy, which constitutes approximately 68% of the universe's total energy content, remains profoundly mysterious. We know it drives accelerating expansion, but its fundamental nature remains unknown. It could be Einstein's cosmological constant, an intrinsic property of empty space itself. Alternatively, it might be a dynamic field that changes over time, sometimes called quintessence. Different possibilities lead to radically different long-term fates for the universe. If dark energy remains constant, expansion will continue accelerating forever, eventually tearing apart all bound structures. If it weakens, gravity might eventually halt expansion or even reverse it. If it strengthens, the Big Rip scenario could tear apart even atoms themselves. Understanding dark energy represents one of modern cosmology's central challenges. Despite decades of observations measuring how the universe expands, we still cannot definitively say what dark energy is or predict its future behavior with certainty. The universe displays a remarkable property called homogeneity when viewed at sufficiently large scales. It appears essentially the same in all directions and locations. This uniformity is puzzling because regions of space that appear connected through shared properties are so distant that light has not had time to travel between them since the Big Bang. Cosmic inflation solves this horizon problem by proposing that the universe underwent exponential expansion in its first fraction of a second. Before inflation, regions now separated by billions of light years were close enough to reach thermal equilibrium. Inflation then stretched them apart faster than light could travel, creating the uniformity we observe today. This explanation elegantly resolves several cosmological puzzles, which is why inflation has become a cornerstone of modern cosmology despite lacking direct observational proof of the inflationary epoch itself. Galaxies don't just move due to cosmic expansion, they also have their own peculiar velocities through space, caused by gravitational interactions with nearby mass concentrations. Our local group of galaxies, including the Milky Way and Andromeda, moves through space at hundreds of kilometers per second relative to the cosmic microwave background. This motion reveals the presence of mass concentrations, galaxy clusters and superclusters that exert gravitational pull over enormous distances. By mapping these peculiar velocities, astronomers can trace the distribution of both visible and dark matter across vast regions of space. These motions remind us that despite the overall expansion of space, local dynamics still matter. Gravity continues to shape cosmic structure, pulling galaxies together into clusters even as the universe as a whole expands. Cosmic inflation not only explains the universe's large-scale uniformity, but also predicts the seed fluctuations that grew into all cosmic structure. Quantum fluctuations during inflation were stretched to macroscopic scales, creating tiny density variations throughout space. Over billions of years, gravity amplified these variations into the cosmic web of galaxies and voids we observe today. This connection between quantum mechanics at the smaller scales and cosmological structure at the larger scales represents one of physics' most beautiful syntheses. The same quantum uncertainty principle that governs subatomic particles also seeded the formation of galaxy superclusters spanning hundreds of millions of light years. Observations of the cosmic microwave background precisely match the predictions of inflationary models regarding these fluctuations, providing strong indirect evidence for inflation even though we cannot directly observe the inflationary epoch itself. Despite enormous progress in cosmology over the past century, profound mysteries remain. We don't know what dark matter is, despite overwhelming evidence for its existence. We don't understand dark energy's nature or whether it will remain constant. We haven't confirmed inflation directly or detected primordial gravitational waves. The universe's ultimate fate remains uncertain. Will it expand forever, eventually contracting, or undergo some transition we haven't imagined? Are there other universes beyond our cosmic horizon? Did time have a beginning? Or does our Big Bang represent a transition from some prior state? These questions keep cosmologists searching, building more sensitive instruments and developing more sophisticated theories. Each answer we find seems to reveal deeper questions, suggesting that our understanding, while vastly improved, remains incomplete. Looking up at the night sky connects us to the cosmos in profound ways. The photons entering our eyes from distant stars have traveled for years, centuries, or millennia to reach us. We see not the present universe, but a tapestry of different moments in cosmic history, woven together by the finite speed of light. The most distant quasars we observe appear as they were over 13 billion years ago, when the universe was young and very different. Closer galaxies show us more recent cosmic history. Our sun's light reveals how it appeared 8 minutes ago. In a real sense, astronomy allows us to observe the past directly, preserved in light. This connection to cosmic history reminds us of our place in an ancient, vast, and still evolving universe, a cosmos that emerged from unimaginable conditions and continues unfolding in ways that inspire wonder and curiosity. As we near the end of our cosmic journey tonight, let's reflect on the extraordinary story we've traversed together. From the universe's first blazing moments to the vast cosmic web stretching across billions of light years, we've explored a narrative of wonder, mystery, and profound beauty. We've encountered lights so dense it behaved like matter, black holes older than stars, and structures so immense they challenge comprehension. We've learned that the universe may be just one bubble in an infinite multiverse, that time itself flows differently under extreme conditions, and that the fate of everything depends on mysterious forces we are only beginning to understand. Dark matter shapes galaxies invisibly. Dark energy drives accelerating expansion. Quantum fluctuations seeded all cosmic structure. These discoveries reveal a universe far stranger and more magnificent than our ancestors could have imagined. Yet for all we've learned, mysteries remain. We still don't know what most of the universe is made of. We cannot see beyond the cosmic horizon. We don't understand what happened at the very first instant or what will happen at the very end. Each answer we find opens new questions, revealing deeper layers of cosmic mystery waiting to be explored. But perhaps this is as it should be. The universe would be less wondrous if we understood everything completely. The mysteries inspire us to keep searching, questioning, and imagining. They remind us that reality is larger and deeper than our current understanding, always inviting us to explore further. As you drift towards sleep tonight, carry with you the knowledge that you are part of this vast cosmic story. The atoms in your body were forged in ancient stars. The quantum fluctuations that seeded galaxies also shaped the matter that eventually became you. You are not separate from the cosmos. You are the universe experiencing itself, conscious stardust contemplating its own origins. In the morning, the sun will rise as it has for billions of years, its light traveling 8 minutes across space to warm the Earth. Stars will continue their slow dances through galaxies. Space will expand imperceptibly. The cosmic microwave background will whisper its ancient message across the sky. The universe will continue its grand unfoldment, indifferent yet magnificent. Somewhere in the unimaginable vastness, perhaps other beings gaze at their own night skies with similar wonder. Perhaps they too ask where everything came from and where it's all going. Perhaps they too feel the strange mix of insignificance and connection that comes from contemplating cosmic immensity. We are not alone in our questioning, even if we are alone in our particular corner of space. The cosmos has given us many gifts: complexity that allows life, stability that permits evolution, beauty that inspires all. We are privileged to exist in this particular moment of cosmic history when the universe reveals its secrets willingly, when evidence of the Big Bang still surrounds us, when galaxies remain visible before they drift beyond the horizon forever. So rest now, knowing that you are part of something immeasurably vast and ancient. Let the mysteries remain mysteries for tonight. Let wonder replace worry. Let curiosity about stars replace the concerns of the day. Allow yourself to feel small beneath the cosmic vastness, yet significant as a conscious part of it all. The universe took billions of years to create the conditions for your existence. Stars lived and died to forge the elements in your body. Galaxies collided and merged, shaped by dark matter's invisible hand. Space expanded, time flowed, entropy increased, all leading eventually to this moment, this breath, this consciousness contemplating its own cosmic origins. May these thoughts bring you peace. May the vastness of space remind you that your worries, however real they feel, are fleeting against the backdrop of cosmic time. May the mystery of existence inspire you rather than frighten you. And may you drift into sleep cradled by the same forces that cradle galaxies, gravity gentle and constant, time flowing steadily onward, carrying you through the night toward morning. Sleep well, cosmic traveler. The universe continues its ancient dance, and you are part of it. Tomorrow, the journey of discovery continues. But for tonight, rest. The stars will keep watch while you dream.